The final activity that we're going to look at in this section is the arc length of polar curves. And suppose we have an arc length, or suppose we have a function r equals f of theta. To be able to find the length over some given domain, provided that it's continuous and differentiable, we're going to use the formula length equals integral a to b of r squared plus the derivative of r squared with respect to theta. So a basic example of this, let's compute the arc length of r equals 2 cos theta from 0 to 5 pi 6. First thing we're going to do, we're going to find the derivative with respect to theta. So dr d theta is going to be -2 sine of theta. And then we just substitute back into our formula above. And so our length is going to be equal to the integral from 0 to 5 pi 6 square root of 2 cos theta quantity squared plus a -2 sine theta quantity squared d theta. And this works out really nicely because this is going to become the integral from 0 to 5 pi 6 of 4 cos squared theta plus 4 sine squared theta d theta. And we know that this, if we factor the 4 out, we would get 4 cos squared theta plus sine squared theta. And we know that's 1 by our Pythagorean identity, which is going to be just 4. And so this now becomes the integral from 0 to 5 pi 6 of the square root of 4 d theta. We know the square root of 4 is 2. That's going to be 2 theta from 0 to 5 pi 6. And that's going to be 2 times 5 pi 6 minus 2 times 0, or 5 pi thirds. A second example, we have r equals theta squared, right? Just to kind of get an idea of what both of the functions look like initially. So we had this function 2 cos of theta, and we saw this one before. So this is going to be a 2 cos of theta. I think we saw 3 cos of theta in a previous video, which was a circle. This again is a circle, okay, radius 1 centered at the point 0, 1. And then if we had theta squared, we basically have like a spiral, okay? Now we're looking at this over the domain from 0 to pi, okay? So realistically, if we just wanted to just cut that out, this is what we're looking for. So this is the length of what we're looking at, okay? It's almost like half of a cardioid if we're just trying to make sense of what's in here, but it's really just a spiral. So we're going to find the derivative, just like we did in the previous. So dr d theta is going to be equal to 2 theta. And then we're going to substitute into our formula. So the length is going to be from 0 to pi of the square root of theta square plus 2 theta quantity square d theta, or integral from 0 to pi square root of theta to the 4th plus 4 theta squared d theta. A trick that we've seen throughout the semester is we can factor out a theta squared and then simplify. So this is going to be integral from 0 to pi square root of theta square from theta square plus 4 d theta. And then the square root of this theta square, since it's a factor, we can just move that on the outside now. So we get the integral from 0 to pi of theta square root of theta square plus 4 d theta. All right, so we can use a u substitution now. So we're going to let u be equal to theta square plus 4. du is going to be 2 theta d theta. And then finally, we can divide by 2. So du over 2 equals d theta, right? 2d theta, or theta d theta, excuse me. And that's precisely what we want. So now we're going to have the integral from a to b, square root of u du over 2, which is the same thing as the integral from a to b. I'm going to factor the 1/2 out, and then we have u to the 1/2 du. We're going to integrate now by adding 1. So we get 1/2 u to the 3/2 divided by 3/2 from a to b. If we multiply by the reciprocal, we have 1/2 times 2/3, excuse me. And then we have theta squared plus 4 to the 3/2. So remember, we had from 0 to pi were the initial bounds. Okay, so we go back up here. And so we simplified just a little bit by substituting theta and 0 back in. 0 does not cancel out the term. So we have 1/3 of pi squared plus 4 to the 3/2 minus 1/3 of 0 squared plus 4 to the 3/2, right? Not much we can do with this. In fact, there's nothing we can do with that. But this just becomes 4 to the 4/3, all right? And 4 to the 4/3 is 8, okay? So if we wanted to simplify this, we could write this as 1/3 pi squared plus 4 to the 3/2 minus 1/3 times 8. And then we could factor the 1/3 out if we really wanted to, although at this point, there's not much we can really do to make it look much better. So that's going to be pi squared plus 4 to the 3/2 minus 8, okay? Or if you wanted to write it back into the radical notation, another way that you could possibly write this would be the square root of pi squared plus 4 cubed minus 8. Okay, so either of these or any of these are fine with me. Okay, I don't really care, just because at that point it's starting to put lipstick on a pig and you can't really make it look much better than what it is. Okay, so that's our arc lengths. Okay, so arc lengths aren't too bad. There's not a lot of arc lengths in polar coordinates that we can find exact values for. Okay, so just be cognizant of that as we're going through. Most of the time in real life, if you're doing this, you're probably going to have to use a numerical method like your Simpson's rule or your trapezoidal rule to be able to approximate what the value of one of these arc lengths are in polar coordinates.